Whee! There you go. Well, first of all, yes. Okay, that looks like it. That's not it? Oh. Oh, your calculator. Oh, I thought you said packet. Okay. You'll be all right. You'll be all right. Can you remember to give this back to me? Can you remember to give this one back to me? Here you go. All right, now what I did with the other class is I reviewed this lesson kind of quickly because we'd already had it. I already reviewed it. But the reason I like this part of the lesson is that hopefully it convinces you why the rest of the world decided to scrap the measurement system that they had developed in their history, and why the whole world uses this system. And it has to be easy, and it is. So they took a meter, and the meter came from the earth itself, right? Then, if you could build a meter stick, you can build a box. Remember this? And what do you call this? How much volume is this? One, what? It is called 1 liter. What else is it called? 1 cubic decimeter. What else is it?
10 cubic centimeters.
I keep looking at your eyes because I need to know what do you think? It's 1 liter. It's 1 cubic decimeter. What else is it?
10 centimeters.
What's 10 by 10 by 10, which gives you what? 1,000 cubic centimeters. Well, we figured out that a cubic centimeter is the same as a milliliter, so it's 1,000.
10,000.
No, it's 1,000.
10 milliliters squared.
No. Okay, now that's a good question. I'm glad you brought that up. A foot is a distance. A square foot is area. A cubic foot is what? Volume. So, I'm glad. Hey, Freddie, I'm glad you brought that up. But what is a gallon? It's volume. So I don't have to cube it, do I? It's a distance unit cubed that is volume, but I don't cube the word liter, do I? I don't cube the word milliliter. Milliliter means volume. Liter means volume. Gallon means volume. Now the other thing this is worth, this is 1,000th of a big cube. What's that big cube? It's 1,000th of a cubic meter. Okay. That's also a million, and I'm glad they didn't send these. Cubic millimeters. I'm glad we don't have those. This box would be a million of them like that. Now, to tell the story a little bit further now, they did something even better. From the meter stick, you made the liter box, and from the liter, if you were to fill that with something they thought every human needed anyway, which is water, right? They said, if you fill that with water, it's going to have a mass of 1 kilogram. Isn't that right? So this much water would weigh the same as this. Do you know why, though, that much water takes up more space than this? Why does this take up less space? What is it?
It's density.
It is. This is more dense. The same amount of mass takes up less space, doesn't it? If I had a kilogram of gold, it'd be like this big. Gold is really dense. Okay, so now that the last 2 pages of the chapter talk about density. What is density? It's the mass of an object divided by its volume. Now, I want you to look at this. This is how beautiful this system was. If you fill this liter of water, it has a volume of 1 liter, but it has a mass of 1 kilogram, right? Well, what's the same as 1 liter? 1,000 milliliters. Or what's the same as 1 kilogram? Now divide both sides by 1,000, and they did this on purpose. For water, what happens? 1 milliliter of water is 1 gram. So if I measured out 50 milliliters of water with this, it would have a mass of how much? 50 grams. Wow, beautiful. It's a beautiful system. And look at this, it's even better. What's the density of water? Let's see, 1 gram, 1 milliliter. What's the density of water? 1 gram per cubic centimeter. That's a beautiful number, because what if you have a density of 3? You're 3 times more dense than water. And you would tend to sink in water, wouldn't you? What about a density of 0.5? You probably float. That's a beautiful system. You get it? That's all I'm trying to show you, that it had to be something that was so easy, and these are all easy. All the numbers are easy, right? Like 1, 1,000. All right. Then what we did next is we kind of switched gears a little bit, and this may not be the drawing your class used, but it's something like it. I drew a line, and I said, let's get into the part of the chapter called measurement. And I had a kind of, not a great ruler. See this? Not a great ruler. Why?
Because it's only got a couple things.
Not too many lines, are there? And these are actually decimeters, aren't they? They're decimeters. So when I put that on there, I said to myself, well, I'm certain that it's 1 decimeter, and I'm certain it's not 2. So therefore, it has to be 1 point something, isn't it? Now, I run out of lines, didn't I? So this thing called significant figures says, if you're a scientist or an engineer, when you measure, you must write every number you're certain about because of the lines. And how many numbers are you allowed to estimate? Only 1. And you put both those together, and you get significant figures. Now, this ruler here then, some of you might say it's 1.3, some of you might say 1.2. That's okay. I know that we both guessed on the last number, right? And guess what else? If I showed this to a scientist in Russia, they would know what the ruler looked like. They weren't even here. And how do they know what the ruler looks like? They say, I know what the ruler looks like. You had lines for 1's place, but guess what? You had to guess 10's place, didn't you? That's right. That's why they use that. You're not going to hear about this in math class. They don't even use measured numbers in math. They use perfect numbers, don't they? Now, when we turn this over, I have a better ruler. What do we find out here? So we know I think that's I'm certain that's 13 and not 14. And I'm gonna guess 13 point whatever. And some of you thought it was 2 or 3 or something like that, right? So notice what happened then. I only had 2 significant figures with the bad ruler. I had how many now? 3. I feel a little better, don't I? And then when I do this ruler here, and I'm not going to take the time to magnify this again, but when I use this ruler, I got something like this. Now, what would a scientist say? You had a pretty good ruler. You had lines for 10's place. You had lines for 1's place, didn't you? You even had lines for what? 10's, but you didn't have lines for hundreds, didn't you? You had to guess the hundreds, didn't you? Does that make sense to you? Now, let me see if it does make sense, because I'm going to ask you to do something. Whoever you're sitting next to, I want you to talk about this, and I have a graduated cylinder here. Now, I'm going to magnify so you can see it a little bit better. We get too much glare there. Can you turn off just the front set of lights for me, please? The other class, I didn't have that much glare. Huh. Oh, that's nice. There you go. Thank you.
That's the back lights. That's what it is.
No, I don't think so. Wait a minute. Hold on.
Oh yeah, let's go. Then just try it.
Yeah,
We'll just try.
Oh, yeah, that's better. That's so much better.
Oh yeah, baby.
Hang
Oh
on.
my god.
Let me try
It's like
something.
night and day.
Let me try something.
Oh yeah.
All right, here we go. Now, whoever you're sitting next to, I want you to write down a possible reading using this graduated cylinder. Write down a possible measurement that you might get from this graduated cylinder. Talk to your partner, and what do you think?
You're not gonna fill it with water, right?
No, I just want to say, talk to your partner. You guys can talk. What's a possible reading that you could get, a possible measurement from this graduated cylinder? All right. Did everybody write one down? All right, let's write one down. And to save a little bit of time, I'll tell you what. Everybody stop. Now, I have lines for the ones place, so I know you could say 6 point something or 7 point something. I get that. Everybody should have the ones place in there, right? I also have lines in between there called tens place. So you can be certain about tens place because you have lines. So I know that 6.1 is not a good answer. Because if you have lines for tens place, what are you forced to do? You have to go to one page past that. So if you had a reading on your paper that went to hundredths of place and you put milliliters after it, then you understood what the lesson was about.
Yeah.
All right. Everybody look. See if you had one. Did it go to hundredths place? Did it have milliliters after it? All right, one more. One more. Okay, ready? Write down a possible measurement you could get from using this graduated cylinder. All right, does everybody have one? All right, now, you have lines for tens place. You have lines for ones place. You do not have lines for tens place, so you would stop with tens place. You would have tens place. So if you had something like 33.5, that's correct, and you have milliliters.
Yeah.
So you should have gone to only tens place. Only go to tens place.
We said 30.
You said the exact same thing. You guys are like connected.
What? You had the same one I said? I just,
Well,
that's weird.
you guys must have
All right, so does everybody understand that? So now, one thing I want to show you that I know this because I've taught at other schools before, but a lot of people will tell you that, oh, I took chemistry, and then you say, well, we're doing significant figures. They said, oh, I hated that. And I think some people do hate it. I don't think you should hate it, because I do actually approach it differently. Number one, most people who did it in school, they were never taught to say where they came from. Where do significant numbers come from? And they come from what? The tool. They come from the instrument, don't they? If I use this one, I may only get 2 sig figs. This one I get 3. This one I might get 4 sig figs. See that? This one I might get, see? So where do they come from? They come from the instrument. Now the reason that you'll never talk about this in math class is because they don't use measured numbers in math. They use a theoretical number. 5 in math is 5.000 to infinity. There is no error. It's the perfect number. But if you're an engineer or scientist around the world, all of them know what significant figures are. They know what it means. So let's take a look. Now, the only thing I didn't like about this handout sheet is they didn't take the time to put little units after it, so you can just make up whatever units you want, but that won't make any difference on how many sig figs. So I'll just put grams after all these. Now, did we start this yesterday? Okay. Okay, now, let's say you're reading someone else's scientific work. You're looking at their data. You were not there. You were not there. You don't know what instrument they picked up. But every scientist and engineer in the world, I do know what your ruler looked like. I do know what your graduated cylinder looked like. But I wasn't there. You know how I know that? Because every engineer and scientist knows the rules for significant digits. So what we're going to do is, I'm going to show you, imagine this is somebody else's work, and I ask you, what did that ruler look like, okay? All right, let's take a look. Did I do any of these yesterday? Okay, let's take a look. Well, I'll tell you, the people, if you talk to other people from those schools, and they said, I hate significant figures because I had to memorize these 6 different rules, and I mixed them up. Well, that's not going to happen here, okay? Let me show you what I do. When I first started teaching, I did teach like the other teachers did, and I could see it. It was like a game. Learn the 6 rules, play the game. How many sig figs? How many sig figs? How many sig figs? Number one, it had no relationship to the real world of science. I'm trying to tell you it comes from the instrument. I'm trying to tell you that every engineer and every scientist know these rules, So you have a certain set of rules to go by that the math teachers don't have. I also used to teach 6 or 7 rules for sig figs. And then I figured out, no wonder they hate this unit, because I don't need to teach you, this rule says you are significant because of blah, blah, blah. This rule says you are not significant because of blah, 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 blah. Well, guess what I figured out? Well, instead of teaching you all the rules, why don't I only teach you the rules that tell you when you're in? I'll only teach you the rules that say you are significant, and guess what? What are all the other numbers? Not significant. So you don't have to worry about the rules about that. So here we go. Number 1, rule number 1, if you're looking at measured numbers, if you see a number in a measurement that's not a 0, you're in. You're in. You said, what? I like this rule. Now watch. We're going to find out how many significant figures. I'm going to do all at the same time. All of these at the same time. Watch. I'm going to put one line here that says you're in. You're in. You're not a 0. You're not. You're in. 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 Hey, if you're not a 0, you're significant. If you're a measured number.
Is this always good?
Oh, there are 3 rules. Now, I just did rule number 1 for all 10 of them. I keep looking at you now. Everybody look at me? Yes? Is there any way you would not understand rule number 1?
No.
Okay, rule number 2. And if you do become a famous scientist, please don't tell them this is called the Oreo cookie rule. I made that up.
Wait, what's
And what happens is, number 2 says, if you are a 0 and you're trapped between 2 significant digits, you're in. Now, you see this? This is not an Oreo cookie. It only has 1 wafer. So there's no trapped zeros here.
oh?
There are no trapped zeros here. I'm going to put 2 lines there. That's rule number 2. I'll never ask you on the test what rule it was. I'll never ask you that. Let's find. Let's try to. No, you're not trapped. You're not trapped. No. Oh, you are.
You are.
Oh, look. No trappy here. Just 1 wafer. Over here. Oh. Triple stuffed Oreo. Now, rule number 1, pretty easy. Rule number 2, pretty easy. Now, I need you to pay attention to rule number 3. If you'll pay attention to rule number 3, we're done. Rule number 3. If you are a trailing 0, and trailing 0 means you come after a significant figure. Okay? Now watch. See this number here? There are no zeros that come after the 2. There are no trailing zeros. And I know you want to look at those zeros. Why? What rule makes you look at those zeros? Rule 1? No. Rule 2? No. Rule 3? No. Don't look at them. Look here, though. This is a 0 that comes after the 2, doesn't it? Now, do trailing zeros always count?
Yes.
No. It says only count if what?
If there's a decimal.
Okay, I can remember that. There's a trailing 0 here, and there's a decimal, so you are rule 3. All right, let's go down here. How about this 0 here? Does it come after a significant figure?
Yes.
Is there a decimal?
Yes.
Then you're in. Look at these. Now this is where I need you to pay attention, okay? This is an honors class. This right here, these are trailing zeros. Do they count?
No. Because there's no decimal.
Right. Now, I also know that scientists are real people. I don't want to fool you. I am a scientist. Too bad you didn't understand. That's not what I want. I'm a person. And so I want to make sure that you understand about my instrument. This instrument, if these don't count, then the total number of sig figs there is only 1. You know what that means to me? That's a terrible instrument you had. That's terrible.
Oh boy.
It went from 0 to 10,000, and you had to guess 5,000? That's what it says. 1 sig fig says your instrument was not very good. But I don't want to fool you. I don't want you to think, well, I wonder if he meant to put a decimal there. So what a scientist would do, here's what they would do. They would put it in scientific notation, and then you only look at this part here. See this? How many sig figs are in that?
1.
I'm letting you know I did not have a good ruler. I did not have a good balance. It was so bad, you only got 1 sig fig. Let's look at the next one. What about, are these trailing zeros?
Yes.
Is there a decimal?
Yes.
Then they're in. Now, again, I don't want to mislead you. I don't want you to say, I wonder if he meant to say 5,000 without the decimal. So what would a scientist do? He'd say what? 5?
5 times 10 to the third.
No. I put 5.000 times 10 to the third. Why? Because I'm telling you, I had how many sig figs?
4.
4. I had a very expensive instrument. See that? I had an expensive instrument. 5.000 times 10 to the third grams. How about the next one? Are these trailing zeros? Do they come after?
Yes.
I had somebody in the last class. They thought I said trailing zeros come after a decimal. No, never said that. I said they come after a what?
Significant.
And these do come after the 1, don't they?
Yes.
Now, is there a decimal?
Yes.
Then you're in. All right. Did this one have any trailing zeros?
No.
No. You go left to, when I go left to right, I don't even start counting sig figs until I get to a non-zero. I don't even look at those. Okay, how about these? Is this a trailing zero? Is there a decimal? Right there. He's in. And no trailing zeros here. Now let's go ahead and find out how many you have. Ready? How many sig figs would this measurement have?
1,
The next one.
2,
The next one.
3,
The next one.
4,
The next one.
1,
The next one.
4,
This one.
6,
The next one.
1, sir. What?
The next one.
4,
The next one.
5.
All right. Thank you for your enthusiasm. I like that. Now, I'm going to finish this part of the lesson by asking you some questions. First of all, do you know that these rules, they'll never be talked about in your math class because they only apply to measured numbers? Okay? The math teacher will not. As a matter of fact, the math teacher will say something like this. If they said, hey, put this in a calculator in math class, you're not going to put 3.00. They'll say you're wasting your time. It's the same thing, right? But in science, this is not the same thing because you're letting me know how good of an instrument you had. And so when you see that, you say, why did they write 3.00? Why didn't they just write 3? You're thinking about math class. So these rules only apply to measured numbers. Next, what if you have a counting number? What if I said you had 3 books? How many sig figs does that have?
Infinite. No, 1.
What do you think? Again, this is a detail. This is some of the detail. 3 books. How many sig figs?
1.
Okay.
Nope. Infinite.
It's infinite. Because it's not a measured number, it's a what?
It's a
It's a perfect number. It's a counting number, okay? Counting numbers go to infinity. They're perfect. They have an infinite number of sig figs. All right, next. Sig figs come from the what?
comes from the science instrument you use to measure.
That's where they come from. That's why I have to communicate with you 12.00. That's a pretty nice ruler. Okay, next. All measurements have 3 things in common.
Error.
Error. They all have error.
After the last one.
Error.
Number.
A number,
Unit.
a unit,
and error.
an error. And the last one, and we're going to move on. When is 3 centimeters not necessarily 3 centimeters?
What?
When is 3 centimeters not necessarily 3 centimeters?
Never.
When it is,
Perfect.
When it is.
Unit.
somebody said it. What? You're close.
Value.
Significant figure.
Does that look like enough spaces for significant figure?
Oh,
Deviation.
Measured. Okay, now, why is it that 3 centimeters might not necessarily be 3 centimeters when it's measured?
Because you're guessing.
Yeah, yeah. So if you had a better instrument, you might find out it was 3.01 or 2.98. You got that?
Yeah.
See, this discussion will never happen in math class. Mathematics is not meant, your class is not meant to talk about measured numbers. Your theoretical number is about the theoretical things in mathematics. This is about the real world of real measured numbers. And we have to have a set of rules that everybody else uses in the world. Now, if you have a calculator, what I'd like to do is I'm going to assign you a problem here. We're going to flip this over. And I do want to correct one mistake. Number 7, it says 150 liters to cubed. First of all, there's no such thing as that. So that was a misprint. So what I like to do is, we have a lot of people here, so why don't, okay, you do number 1. And what I want you to do on your calculator, do this problem in your calculator, and you're going to put it right there. And you're going to do number 2, and 3, and 4, and 5, and 6, and 7, and 8, and 9, and 10. Okay, now, the rest of you, you can do any one you want. You can do any one you want. So let's go ahead and take about a minute, and let's do the calculations. And then I'll teach you the lesson that goes with it. All right, is everybody ready? I'm going to mention again that you're not here just to sit here. You're here to be engaged, and when we talk about something, you want to think about it. You want to think about what we're doing. What we're doing here, you'll never do in math class. This is something that's very specific to science and engineering. All right, ready? Give me the actual number, kind of slowly, and what the calculator said. Okay, now, everybody listen. The calculator did a good job on that. The calculator is so dumb, it did not know what a meter times a meter was. What is a meter times a meter? What is it? Right, also known as a square meter. That means somebody is calculating the area, aren't they? A meter is distance. What's a meter to the second power? It's not distance, it's area. What's a meter to the third power? Volume. So distance units are not distance units if they're squared or cubed. On the other hand, we do have some things like gallon. Gallon by itself means volume, doesn't it? Liter by itself means volume. I don't have to cube those. All right, let's go to the next one. Go. 24.642857114. And what in the world is a meter squared? A square meter divided by a meter. What is it? Meters. All right, next, number 3.
How do you get me?
This is like in math. What is x squared over x?
So it's like, what is 2 divided by, no.
Okay, ready, go. Next one, third. Lily.
No.
I can't hear, wait, I can't hear. What is it?
53.21.
And what's a milliliter plus a milliliter plus a milliliter?
Milliliter.
Yes. Next one. I'm going to tell you why we're doing this. We're not just doing it for math. I'm going to tell you why we're doing it. Go ahead.
26.56 grams.
Yes. All right, next one.
6.72672 centimeters cubed.
Yes. That means you're measuring volume, isn't it? Next one. I'll make sure. Okay, go ahead. Freddie.
Oh, is it me? 3.351 centimeters.
Okay, next one.
37.5 meters squared.
There's a misprint. Remember I told you that? So what's a liter divided by a liter? What's a liter divided by a liter?
Liter.
No.
Negative liter squared.
All right, what's, in math class, what's this?
1.
Yeah, because they cancel, right? So what's a liter over a liter?
Nothing.
Nothing. So no units. Next one. Yes. All right, next one.
1.727.
Wait, is this scientific notation?
Oh.
What is it?
1.727.
Oh, the other class got something different. I do number 9. Oh, well, they gave me the wrong answer. What is it then? 1 point what? 1 what?
1.72776.
1.737.
727.
Oh, go again. 1.7,
2776.
like that. Okay, and what's your units?
Meters cubed.
Okay, and the last one?
89577.3463.
Wow, too fast. 895 what?
77.34632.
Units?
Meters.
Yes, very good. Now, I didn't want you to do this because I'm trying to see if you know how to use a calculator. There's a set of rules that go with measured numbers. We already figured that out. But another group of people said, as a scientist, what if I have to do calculations with measured numbers? Your math teacher, if you write this down in your math class, you get a gold star. Wow, you wrote down exactly what was on the calculator. You got it right. This would be correct in math class. This would be a big fat lie in the world of science and technology. Because, look what I'm saying, look what I'm doing here. You're telling me that you had a calculated number that went down to tenths, hundreds, thousands, 10,000. You're telling me you know for sure that 100,000th place what this number is going to be, when none of your numbers, none of your measured numbers were that accurate, were they? So you're lying. So a group of statisticians got together with scientists a long time ago, and they said, what are the rules for calculating with significant figures? And here they are right here. Look at the top. When you're multiplying and dividing with significant figures, you have to limit and round the answer to the least number of significant figures. So let's take a look. I am multiplying here. How many sig figs are in this one?
2, 3,
3. How about this one?
4.
So what's the least number?
7,
3.
3. Gosh.
Okay.
Three's
The least number between 3 and 4.
7.
No, it's 3. 3 is the least, is the smallest number between 3 and 4. Now please pay attention. Can I get finished here? All right, watch. All right, wait till everybody's ready. You're not allowed to write this in a science or engineering. It's a lie. It says I have to round it to 3 sig figs. So watch here. Here's the first sig fig. Here's the second. Here's the third. Now, when you round to 3 sig figs, do you ever look at the fourth one?
Yes.
You have to.
Yeah.
See, some people think round to 3 means chop. You don't chop to 3, you round to 3. So when you round to 3, you have to look at the fourth one. Now watch. If that fourth one's 5 or higher, that 3 there is going up. No. Okay, now. All right, now listen carefully. Listen carefully. This bothers some of you. It bothers you a great deal because you cannot. It tears you up to write 3.33 because no, it's not exact. No, you're talking about math class. And when you're dealing with perfect numbers, then this is the answer. When you're dealing with measured numbers, this is a lie. This is the truth. Let's do the next one. The next one's a division problem. The good news, multiplication and division has the same rules. Ready? How many sig figs are in that?
4.
How about here?
6 total.
2.
What's the least number?
2.
All right, watch. Ready? 1, 2. Do I look at the next one?
Yes.
You have to.
25.
Oh, yeah, I'm big enough.
Yeah.
All right, here we go. 25 what?
Meters.
All right, next. We're going to skip that one and we'll come back to that in a minute. Let's go to another multiplication problem down here, number 5. Now, ready? How many sig figs? Don't break my heart on this. How many sig figs? 2. Very good. This one.
2.
How about this one?
4.
The least number?
2.
Okay, here we go. 1, 2. Take a peek. No, not big enough. All right, let's find another one. This is a division problem. And how many sig figs in that one? Oh, careful, careful. How many in 150? Huh? 2. How about here?
1.
Okay, 1. Now watch. This is where you're going to make a mistake. Am I going to lose the next number?
Yes.
I have to.
4.
Oh, I'm big enough. Now, I don't know why. I've seen people do this. Look at me. Oh, I want you to round off 37.5. Yeah. What is it? 4. That's stupid. 4 is not anywhere close to 37.5. You mean this, don't you? I have to round to 1 sig fig. How many sig figs does that have? How many sig figs does 40 have?
2.
What rule? Tell me what rule. Tell me what rule makes that significant. Is it rule 1?
No, that's one significant thing.
It is. It is. Isn't that right? Yes, no?
Yeah.
Now, we're having a little bit of fun. Listen, we're having fun, but you can't round off 37.5 to 4. That doesn't even make sense. Next one. Down here, this is a multiplication problem. How many sig figs? Go. How many?
2. No, you're on a different one than I am.
Number 9.
4.
4. How about this one?
3.
Yes, this one.
2.
Okay, ready. 1, 2.
2.
No, not big enough.
No dice.
And the last one, in the scientific numbers, you only look at the first part of the number. So 4 sig figs. How about this one? How about the second one? 5. The least number is 4. 1, 2, 3, 4. Oh,
Yes, sir.
wait a minute. That means this is going to be an 8, right? 8, 9, 5, 8. Did I stop there? No way. How can 89,000 be round off to 8,900?
0 out of 0.
We don't.
Yes. How many sig figs are in that?
A lot.
2. 4.
4. Okay. Now, last thing, one more minute, ready? I'm not the statisticians, but the people who do statistics said, I'm sorry, but if you want to be true, if you want to use measured numbers and be truthful, the rule for adding and subtracting, I'm sorry, it's got to be different. It says here, when you're adding or subtracting, you have to round to the least number of what?
Decimal.
Not sig figs, but
Decimal.
okay, so let's do one. Ready? I'll do the first one for you. This is adding, right? This goes to hundreds place. This went to tens place. This goes to ones place. What's the least number of places? 1. The ones place. So ready? When you round to the ones place, do you ever look at the tens place?
Yes.
You have to.
You got to.
Oh, not big enough. Not big enough. Okay, ready? And one more and we'll be done. Ready? I don't count sig figs. Hundreds place, tens place. What's the least number of?
Tenths.
By the way, every place value is a decimal place. I didn't say the right of the decimal. Every place is a decimal place. Tens place, right? Let's round this into tens place. And if I round to tens place, do I ever look at hundreds place?
Please do.
I have to.
Unnecessary roughness.
All right. That's the lesson. And